introduced that this will be an hands-on machine learning session using Python. And basically, we won't be coding the different models from scratch. Rather, we will be using some of the libraries which are quite this popular in the machine learning world, and we will be using those only. Uh, Doctors, where there is no annotation tool, I think. Just give me a second. Okay. Fine. Anyways, so the topic which I have given to this talk is machine learning. This is a machine learning simple tutorial, and the way I'm going to cover this whole topic is, and I have been given around 30 to 40 minutes, and I hope to cover all of this in these 30 to 40 minutes. So I will start from data, and I will discuss the various aspects, what we need to do and how the data can be input in the system, and then discuss the dependency between data and the model, and later on go on to importing the data, incorporating the data into our system, and then finally feeding that data into our models. And the last step is that we will test we will train our data and then test it on our test sets. we I have one more little topic for you at the end. If time permits, I will discuss it, and that is called as the hyperparameter search, and we will discuss that as well if time permits. Now, uh, the way I have organized this tutorial is using some of the most popular machine learning libraries or data science libraries which we people use in the machine learning community, and those include a library, those revolve around the main library is the scikit-learn library. It's a fairly common and well written machine learning library which is used for a variety of tasks, right from the core task of learning, training the various machine learning models like your uh, decision trees or the SVM or the logistic regression or the linear regression, and similarly the Bayesian classifiers, the new Bayes, the multinomial Bayes classifier. Similarly, for clustering purposes, you can have k-means, you can have Gaussian mixture models, and then you can have random forests. You have some basic neural networks as well, and all of those things are incorporated into the scikit-learn library, and it's a very good library which I recommend all of you to be well versed with it. And the biggest advantage of it is that it has a huge there are two advantages to it, and the reason why I intend to introduce this machine learning library for this session is for two reasons. One is that it's very well written, its documentation is very clean and easy to understand, and whenever you have any problems, you can just go to its site, and you can learn about the various models. There are many tutorials also available, and many examples have been incorporated to the documentation into the official documentation. Second is the online community, and there is a huge online community which you can find help from, ranging from either Stack Overflow or Medium posts or Reddit or some other places as well. So this will be our central library, and around this library we'll be using two other important libraries, and those are NumPy for the mathematical computations or the scientific computations, and the other one is the Pandas for basically the explorative analysis of the data. Fine. So and I expect that all of you will be well aware with some of the basic terminologies of the machine learning, like what the data means, what the test set, train set, and the validation sets mean, what does a model mean, what does accuracy mean. So the underlying prerequisite of this tutorial is that the audience is well versed with these topics. Fine. So the first thing is, as you all of you know, that for doing any machine learning project, we must have the data. And the format in which we have to put the data is dictated by the model we are going to use. So if or or in other words, the library through which we are going to train a particular model. Now, one important characteristic of the scikit-learn library is that it has a consistent interface. So no matter what classifier you use, all of them have the same interface. So what I mean by that is that whatever estimator you use, that whether you are linear regression, logistic regression, any model you use, you create its object by calling it a simple constructor. Fine, that is the first step. The second step is for training. All of them have the same function or the method for training, and that is called as the fit method. Then finally, once the model is trained to predict on the test set, all of them have the same method called as the predict. And similarly, if you want the probabilities, it has the predict proba method. Fine. So this is one of the biggest advantages of using scikit-learn, that everywhere there is a consistent and uniform interface which has been provided to the user. And mind you, that other deep learning libraries have been designed by taking inspiration from scikit-learn itself. So like your Keras, which is very much a popular top level library in deep learning community, its design is inspired from scikit-learn. And other libraries are also inspired from scikit-learn, like scikit-image, etc. Fine. So what I was saying is that the model or the shape in which we have to put the data is dictated by the model. Since we will be using the scikit-learn expects our data for any of the estimator we will use. By estimator, I mean either a regressor or a classifier. The data should be in the form of this number of samples and then number of features. This will be the shape. So number of samples means the number of data points we have, and then so it should be in the form of a matrix, where the rows will be having, each row will be one data point, and the columns will have the different features which our data has. Fine. So that should be our first job in any machine learning project we do. Fine. So to incorporate our into our pipeline, we will use the pandas library. Now, why do we use the pandas library? Now, for most of the simple cases, or most of the machine learning cases, our data can either be in the form, can be in a tabular form. When I say tabular form, you are most familiar with the databases relational databases we have. And then the data is in the form of a table where rows represent one record and the columns represent the different attributes or the features. And in machine learning, we mostly store this data either in SQL, but other forms are also available. Like the data can be stored in text files in formats like CSV, TSV, JSON, XML, or simple Excel sheet, or some other binary formats. Fine. The most common scenario is for the data to be stored in a CSV file. CSV, when I say CSV, it means comma separated file, where each record for a particular record, the different features or attributes are separated by commas. So just like I have given an example here. So feature 1, comma, feature 2, comma, feature 3, so on and so forth. So this whole represents one record. Similarly, different records will be there on different lines. So each line will be one record, and each record will be the values will be separated by commas. Now, pandas has the table equivalent in pandas is called as a data frame, and pandas has this method called as read CSV to read a CSV file into pandas and make a data frame out of it. Fine. And then you might simply ask, oh, okay, why do we need pandas for that? But why can't we simply open the file and open the simple text file in Python and then parse that file line by line, split by commas, and get the different values? Now, the answer is twofold. Firstly, it's a very tedious task. So you have to write some long code, and you have to first of all open the file. You have to take care of closing that, and then you have to read the file line by line, and then you have to, for each line, you have to split that particular line by commas, and then extract the different fields, and then you have to convert those fields into their data types. Fine. because by default they will be strings only. So this is a lot of hassle, and pandas, by simple one line, it makes easier for us. Second is that, which is more important, is that it's not just opening up a CSV file and getting it into the memory or opening it. Rather than, there are other explorative analysis which which we might want to carry out on that data before going on and doing machine learning. So like we might want to understand the data, what is the mean of the data. We might want to get the different descriptive statistics from it, like mean, mode, standard deviation, etc., to understand the data better. We might want to plot that data for understanding it better. Fine. So pandas has all of these things incorporated into it. Fine. So that's why it's better to use the pandas, but you can very well do without using pandas as well. Fine. So for our purpose, for demonstration purpose, I'm using a toy data set called as the iris data set. So many of you might be well aware of this iris data set, and it's available on this link which I have given, and I will share this notebook with you people on this link. So, and for the runtime, I'm using the Colab notebook. So I also expect you people to be familiar with the Colab. Fine. So if I run this, so here I am just getting this this iris data set into my into my local drive on, obviously, on Colab. So if I run this, so it is downloaded, and on the left side you can see there is this iris.data, and that is what my data looks like. Fine. So then I might want to just simply print this text file. So I can simply run this cat iris.data. So you can see now it has read the different, it has read this CSV file, and this is the CSV file which has not read, it has just downloaded this, and this is the CSV file that is stored on my local drive. So you can see here each record that there are 4 attributes. So this is like sepal length, sepal width, petal length, petal width, and then the class. And there are in total 3 classes: iris setosa, iris versicolor, and iris virginica. And then there are 150 total data points in it. Fine. So now what I will do is I will use the pandas library to read this file into my local runtime. Right. So basically I had already downloaded it. I again downloaded it. That is why this iris.data.1 came here. So now I will simply do import pandas as PD. So one thing is that if you are going to use the Colab, all of these libraries are already installed on the Colab runtime. So like NumPy, Pandas, scikit-learn, and Keras, TensorFlow, all of them will already be downloaded, will be installed on our Colab runtime. Fine. Anyway, and the second thing is that if you see here, this iris.data CSV file, it does not have headers. Okay. So when you read a CSV file into your pandas data frame, then there is a facility that you can have that header as well. So that's what I am doing here. I am defining a list of features like sepal length, sepal width, petal length, petal width, and finally the class. And then I am using this method of the pandas.read CSV, and I'm giving you the name of the file because it's in my local folder. So it is in the current directory, and the name of the file is iris.data. And then I am telling it that there is no header in the file, and you have to get the header from this features, right? Features list which I created. So if I run it now, Control Enter is short for running. Now, if I want to get the first few, first 5 elements, first 5 records, I can use this method df.head. Similarly, there is another method df.tail, and that will give you the last 5 records. Okay, there is some comment. Okay, fine. So if I do df.head, you can see here now. So you can see the first column. This is just the index to the different records. Fine. So 0 is the first record, 1 is the second. So pandas gives us a facility to even use different indexing for these records as well. So instead of using the default 0, 1, 2, 3, 4, I would request you people. Okay. So I request you people to mute your mics. Fine. So I was saying that pandas gives us a facility to index, give us a custom index to each of these records as well. But here I will be using the normal 0, 1, 2, 3, 4 indexing. And then you see here, the header is also incorporated here. The first record or the first column is sepal length, then sepal width, petal width, and class. Fine. You can even get some information about the data set as well using the method info. So here I am using df.info. Mind you, df is the data frame which has been created from reading the CSV file. So now here it showed me some information. So range indexes, there are total 150 entries, and their index goes from 0 to 149. Total number of columns is 5. Sepal length, its data type is float. Similarly, width, length, height, and the class, its data type is object. Fine. So the data types used are total float 64 are 4, object is 1, and the total memory usage is 6 kilobytes. Fine. Then you might want to get some descriptive statistics from the data like mean, mode, the percentiles, the first 25, the next 50, etc. For that purpose, there is this method called as df.describe. So if I do df.describe, you will get here, okay, there are a total of the total count of the sepal length attribute is 150, sepal width is 150, etc. Mean of sepal length is 5.84, sepal width is 3.045, petal length, petal width. Similarly, standard deviation, minimum, maximum, all of these things will be done with just a single command. Fine. But then we don't need this data frame for our machine learning model. Rather, if you remember, I told you that our scikit-learn expects our model to be in the form of to be in this form: number of samples and number of features. It's an array like, it expects our data in array like format. For that purpose, we'll be using the numpy arrays, and there is a method to convert the data frame into a numpy array with this to numpy. And it's not just converting into numpy, you can even convert your data frame into and save it as a CSV file or a TSV file or a JSON file or different file. And you have different two methods for that. So like you have two CSV, two JSON, and so on and so forth. Fine. So if I now do data equal to df.toNumpy, then data will get the array form of this whole data. So if I do that here, so if I insert another cell and I say data dot, or I just display the data, you can see here now all of that is now as a numpy array. Fine. So this is an array, and this is a multi-dimensional array, and 5.1, 3.5, 1.4, 0.2, and then there is a string iris setosa. Fine. Okay. Then we will be now using the numpy, and it's better to introduce a few aspects of numpy. NumPy is basically used for doing mathematical analysis of vectors, matrices, and other higher order tensors. Fine. So you have, so therefore NumPy provides you the facility to create these NumPy arrays. So all of them are called as the NumPy arrays. So whether this is a vector, it's a matrix, or a tensor, all of them will be called as NumPy arrays. So these NumPy arrays, the NumPy provides methods for creation of these NumPy arrays, and they can be created either from lists, or you can create them from other NumPy arrays. You can even create some basic arrays as well. Then it gives you facility to do different operations on these NumPy arrays, like you can add them, subtract them, multiple, divide, square root, you can get the sum of them, etc. And then finally, it gives you the methods to access these NumPy arrays in efficient manner as well. Fine. So the way to incorporate this NumPy is simply use import NumPy as MP. And then I am giving here, by the way, the number of dimensions a particular NumPy array is called as the rank here. So the rank here has a different meaning than the rank in linear algebra. There the rank has a different meaning, but when we talk in terms of NumPy, rank just means the different dimensions. So a matrix has rank 2, a three-dimensional tensor has rank 3, a vector has rank 1, so on and so forth. Fine. So here I'm going to create a simple array, simple matrix, 3 cross 4 matrix, and it's here represented as a list of a list, and from this list of a list you can create this simple array, and I am naming it A, and I simply saying np.array and then pass this list here, and that will create this numpy array. Fine. Then you can access the different parts of that numpy array. So this is called as slicing. So you can even access individual numbers as well. So I can I can say, just me, if I add a code here, so I can say A, if I want to get the 6 here, so its index is row number 1 and column number 1, so I can say 1 comma 1, and it will give me the particular number 6. But there are other methods in which you can get a range of values, and the technique there used is called as the slicing. You can get slices of this matrix. So for example, if I want to get the first row, I can say, okay, give me the first row A of 1 and all of the columns. So this colon tells that it's all of the columns, so it will give me 1 comma, and this will give 5 6 7 8. If I want that, okay, I want the first row but column number 1 to last, I can say 1 and then up to the last, and you can see I will now get 6 7 8 9. Fine. So I request you people to study this slicing in more detail, because I can't go into much more detail here. Here I have just given you another example that you can get a sub array from this array here. So you can say, if I want that, I want all the rows from 2 onwards, row number 2, and that is only the third row. And then the columns, I want the first, second, and third column. Fine, because there are 4 columns, so first, second, and third. So that's the index I am using here. A, that means up to the second column. The first 2 columns. Sorry, the first 2 rows, and the last 3 columns. Fine. So if I run this, you will get a sub array. So B, and if I display this B now, it will be 2 3 6 and 7. Fine. Similarly, so since this slice, when you take a slice of an array, it basically is just a view, and it's a new data is not created, rather the data is there in place. That means if you now change this slice, the change will be reflected onto the original array. So this should be kept in mind, and many times we make this mistake. So just like here, I have taken a slice B here. Now if I change this slice and change the value to 77, you can see that it reflects this on the original array. So if I do this here, 2 and 77. So A of 0 1 was earlier, A of 0 1 was earlier 2, but now it is 77. Fine. Okay. So one more important point is that if you mix slicing and integer indexing. Integer indexing is simply, I use 1 comma 1 here. This is called as integer indexing. If I get the single point from the array. But if I mix integer indexing and slicing, then the rank will be reduced. Okay. So for example, if I do it here, 1 comma 1, or if I say 1 comma all the up to the first row, then you can see here now, if I use the shape method now, you will see that the rank is 1 comma. That means a rank has been reduced. Fine. But if I again use here 1:2, I use the uniform slicing in both the dimensions, you will see that the rank will be the original rank. So you will see here, it will now be 1 comma 1. Fine. So there will be 2 dimensions. I hope you understand it. If you don't understand, you can then later on ask me this question to explain it better. Fine. There are other ways of creating a numpy array, like ones, zeros, full I random, to create the array of ones or zeros, or a constant array, or an identity array, or a random array. Fine. So all of these are available. Similarly, there are some other methods available which you can run on a particular numpy array, like sum, to get the sum of a particular numpy array, and you can even get some along a particular axis as well. Then minimum, maximum, argmax, argmin, count, and there are countless other methods available. Fine. So now we have this data. So if you see earlier, we converted our data frame which we read from the CSV file into the NumPy array called a data. But now, as you know that our data should be in the form of the data points and the corresponding labels. Fine. So we'll split, and but here in our data, all of them are in the same. All of them are in the same same NumPy array. Fine. So we have to basically carve this part out, call it Y, and these four features should be X. Fine. So that's what we have to do. That's what I have put the title here, splitting the data into X and Y. Fine. So if I initially see the data shape, it's 150 comma 5, but my original attributes are only 4: sepal width, sepal length, petal width, and petal length. Fine. The fifth one here which shows here is basically the class. So I have to separate the class part out. Fine. So that's what I am doing here. I am saying X comma Y is equal to data of, I want all the rows. Fine. I want all the rows, but I want all the columns except for the last one. Fine. Except for the last. -1 represents the last. So you can come back from and the indexes there will be -1, -2, all the way up to 0. Fine. And in the Y, I want to put all the rows but the last column. Fine. And then you can see the X shape and the Y shape here. So now you can see the X has 150 cross comma 4 attributes for total of 150 records, and the corresponding labels are 150 labels. Fine. And you might sometimes want to convert this. So if you see the Y here, so let me show you the Y. If you see the Y array here, it's an array of strings basically. But many a times some models might be such that they don't work with the text well, and you have to convert this into the integer numbering. So like iris setosa will be 0, iris versicolor will be 1, and iris virginica will be 2. Okay, somebody raised a hand. Okay, ma'am, you can go on. Was it a mistake or?
If anyone has any questions, please post that in chat. And
Fine.
if you want directly to ask questions, at the end you may raise your hand.
Fine. Okay. So that's what I was saying, that we might want an integer coding for our classes rather than directly using the labels. And in this code, that's exactly what I am doing. What I'm doing is that I'm using a concept in Python called as the list comprehension. Fine. If you find this difficult, you can go with this part of the code. But basically what I'm saying is that I am checking each and every label. If it is iris setosa, I am replacing it with 1. If it is versicolor, I am replacing it with 0 and then 1. And if it is the virginica, I am replacing it by 2. And I am going through all of the labels in my Y array. And then finally, I'm creating a list out of it, and I'm converting that list back into the array. And that list I'm again assigning it to the Y. Fine. So now again, if you want to see the y.d type, earlier it was object, but now it is integer 64 now. And the array has been converted into 0, 1s, and 2s. Just give me a second. I have any question. Sorry, I had an important call. Anyway, so we sometimes this step is important, but for scikit-learn purposes, this step is not important. Fine. So this is an optional step here. Now, there is one caveat which I want to tell you people is that this iris data set is a toy data set, and many of you might be aware with it. Rather than, and in scikit-learn, many of these toy data sets are already available in scikit-learn in this package scikit-learn.datasets. So iris is also available there, and there are other data sets also available, like the MNIST data set in maybe a post processed form, like the diabetes data set, or the house pricing data set. All of those toy data set which people play with to learn the different concepts are available in scikit-learn as well. So you can very well use that process here in this case as well. So here I have done that. So you can use from scikit-learn.datasets import load iris. So load iris is the method which you can use to load the iris dataset, and then you use that method. So I say iris dataset equal to load iris, and this dataset has then two attributes. One is data and other is the target. Data contains all of these four features of the 140 150 data points, and the target contains the corresponding labels, and those labels here are already converted into 0, 1 and 2. So if I now run this cell, you can see here there are 150 data points here. Fine, 150, and the array is this. Fine. So 0, 1, this is the target array. Fine. Now this is how, so this basically covers how you can get data, but there should be one disclaimer that it's always dependent upon our problem. There is no one method to get the data into our there is no one method to get our data into our system. Rather, it is dictated by the problem at hand. So like if you are doing deep learning and if you are doing deep learning and you are working with different images, then the problem there is a different, and there are different ways of handling and incorporating data or importing data into your pipeline. Fine. So this is the most common scenario here if your data is small and it's textual or numeric in nature. But if you have different types of data like text data, or let us say the image data, or some other data in raw form, then you either have to do feature extraction from it. Fine. Just like we have here, the features are extracted from these flowers in the form of 4 attributes, or you then have to use some other methods. Fine. So this is not an exhaustive way, rather this is one of the ways. Maybe yes, most common way, but only one of the ways. Fine. So once we get the data, we then have to split the data into test, train, and validation subsets. Why do we need to do that? Is basically we want to train our data set on some data set, and then we want to evaluate on other data which the model has not seen yet, so that the evaluation is unbiased. Fine. That's why we usually want to split the data into these 3 subsets: train, test, and valid. Now in our case, we again use the scikit-learn again provides one method for making this easier for us, and that method is this train test split method. It's available in the sklearn.model selection.train test split, and there we just have to pass the array which we have to split, and maybe some other attributes like what should be the size of the test size, test set, etc. And in our case, what we will do is we will break our arrays into 3 subsets: train, valid, and test. And train we will keep as 70%, validation will be 10%, and test will be 20%. So this will be done in 2 steps, because the train test split only splits into 2, train and test. So in the first step, we will carve out the train 70% from the 70% of this data, and we call it train. Then in the next setup, the remaining 30% will again be split by 66% as test and 33% as valid. Fine. So that's what I am doing here. First, I'm importing this train test split. Then what I'm doing is I'm calling this train test split on X and Y. Fine. Because this should be done on both the X and Y should be passed at the same time, because in addition to splitting our array into train and test, it also shuffles the data. Fine. So it randomly permutes the data and then returns that in different permutation. So if we do it differently for X and Y, then the labels will not be correct. So that's why it is important to pass both of them at the same time. So correspondingly, it will give us X train, X test, and Y train, Y test. Fine. And here I have mentioned only one attribute here. That test size should be 30%. Fine. 0.3 is basically 30%. So in this step, I got the 70% data of xtrain and xtest. So if I print it here, xtrain.shape and xtest.shape, it will be the 30%, sorry, 70% of 150, that comes around 105. Fine. And the rest of the 45 will be in xtest. Now this xtest I again take and I again split it into 66% as test set and 33% as validation set. So I say xvalid, xtest, and then finally I print the different shapes. So if I run this now, you will see that xtrain will be having around 105 data points, and correspondingly 45 will be that in the test, the first test, which I am further splitting. And similarly the y train and y test, then when I am doing the second split, then x test is 30 samples, and the validation is having 15 samples. Good. Fine. Now that is basically, we have all the data now prepared. Now we move on to the actual classification. Fine. For that purpose, we have to create a classifier, call on the fit function, fine, fit the classifier onto our data, and finally we will test it on our test data set. Fine. So for this purpose, I am going to show you, for showing you the different, that for showing the power of sklearn and the uniform interface it gives the programmer, I am training 4 classifiers. One is logistic regression, linear SVM, the other SVM. Fine. So this linear SVM is only linear in nature. There is no kernel function used, for those of you who know the support vector machines. And in SVC, you have different kernels. You can mention the different kernels. So by default, there is this RBF or the Gaussian kernel here. But in linear SVC, there is no kernel used. Fine. It's just the normal SVC. And then I'm also using the KNN classifier. Fine. And these are, I must admit that it would have been better if all of these classifiers were in a single package, but due to other reasons which are very well, which are legitimate reasons, they are in different packages. And whenever you have to use some classifier, you can simply do a Google search, just like if I want to use a decision tree. So decision tree in sklearn, I just search it and it will show me where this is. Fine. So you can see here decision tree is in a tree.decision tree classifier. So if I want to use a decision tree classifier, then I will simply use sklearn.tree.decision tree classifier. Okay. So once I import all of these methods or classes, then the second step is to create the objects of these classifiers. So I'm creating 4 classifiers here, logistic objects of 4 classifiers. So logistic CLF is logistic regression, linear SVC CLF is linear SVC, and SVM classifier is simply SVC, and KNN classifier is simply KNN. One more thing you can do is you can pass different parameters here. So if I show it to you here, so if I run this first, so you can, should be available. So now you can see there are different parameters here, like penalty you can mention, loss, the tolerance limit, or the penalty term in the SVM, the C parameter. Similarly, multi-class, because SVM is basically a binary classifier. For doing multiple classification, what is the strategy used? You whether use one versus one or the one versus rest, or the other parameters as well. Similarly, if you see in KNN as well, there will be different parameters, like the nearest neighbor, how many nearest neighbor have to use, what is the value of the K, or some other methods as well. Fine. So just like nearest neighbors, by default there is 5, weights are uniform, algorithm is auto, leap size. You can read about these on your own. Once we create these objects of these classifiers, then we have to train them. And for training, all of these classes provide us the fit function, right? And to the fit function, we have to pass the training data set, the training axis, and the corresponding label is Y. Fine. So that's what I'm doing here for all of these classes, logistic CLF.spit, and I'm passing xtrain, ytrain. Similarly for linear SVM, for normal SVM, and for the KNN. So all of them I'm passing the I'm passing this parameter. Fine. One important thing which you must also take into consideration is that many of these classifiers, they employ or they incorporate or they use the multi-processing capabilities. For many of them, the multi-processing capabilities are available, and wherever possible, you should take use of that. And for that purpose, you have to basically mention that in the classifier itself. Fine. And so just like if I'm able to show, I don't know whether that is possible. uh, uh, just give me a second. Just sorry for keeping you waiting. Anyway, so what I was saying is that many of these classifiers incorporate the multi-processing capabilities of your system. Just like the system I am using is a 4-core system, so I can use the 4 cores at the same time. And for this purpose is this parameter here, number of jobs. You can mention it here, and by default, and if you mention, so like if I mention 8 here, the training process will be done by 8 threads parallelly. Fine. So the multi-threading support is built in many of the library, many of the methods or the classifiers here in Sklearn, and wherever possible, you should take use of that. Fine. So once I do that, I have to then train it. So I will call the fit function of the different classifiers. So there is this for the linear SVM, it shows us this warning that it had failed to converge into the predefined number of steps. The number of steps, again, you can mention in the linear SVC when you create the object of this classifier. Fine. Similarly, this k-near, the k-neighbors classifier also has given us this information here. Fine. So once you train the classifier, the next step is to test it. By the way, what I have done is, rather than calling the fit function individually, writing 4 lines, you can code smartly. I have created a list of these classifiers. So CLF is equal to logistic classifier, linear SVM, and KNM, and then simply use a simple loop and call a fit function. Fine. So rather than writing it this way, you can write it more smartly like this. If I run it, it will achieve the same. Fine. Then we have to get the predictions. Fine. So we trained it on the training data set. Now we have to evaluate it on the test set. Fine. So again, what I'm doing is, and whenever we predict, each classifier will give us a set of predictions. Fine. And I will store those predictions in another array. Why? Basically, I have done something wrong here. Should not have done this. But anyways, I am creating another list, ypreds, and there I will be storing the predictions here. Fine. So what I'm doing now here is, for I comma CLF equal to enumerated classifiers. Fine. So I gives us the index, and CLF will give us one of the classifiers in each iteration. Then I'm simply saying the predictions of I equal to classifier, which is one of those classifiers, iteratively dot predict function. So again, see the beauty of sklearn, that predict is available for each classifier. Fine. So there is no mismatch in the interfaces which have been provided. Fine. And I will test it on the test data set which I have earlier created. So if I run this now, my ypreds will now be containing the prediction. So if that I can show you here. So if I add another cell here, so if I say ypreds, and if I see the type of it, or I want to see, for example, the first, and I want to see the shape of it, you will see it's a 30 comma. So there are 30 values. And if I want to just simply see what is there, the labels are here. So 1111, 00, 222, so on and so forth. Similarly, it has four components to it. Fine. So that I can show you if I run the, if I use the len function of the list. So you will see the length of vibrates is basically 4. So against 4 classifiers, there are 4 sets of labels that have been predicted by those 4 classifiers. Fine. So once we get the predictions, the other step is how to interpret those results. And we usually employ some metrics like accuracy. In some other cases, we might have other metrics like the other commonly used ones are like the recall, precision, and F score. Similarly, there could be some other measures as well. One of the most commonly used metric for evaluating a particular model is the accuracy. So again, can use the sklearn's accuracy score function, which is available in the metrics package. So that's what I'm doing. And again, I will store the accuracy in a list from the corresponding to the 4 classifiers. So the first thing I'm doing is I'm importing this accuracy score function from the matrix package. Then again, using the same strategy, I will go over all of these predicted data set, predicted labels, and compare them with the original label, that is the y test, and then get the accuracy. So if I do that, if I run this, you will see accuracy for logistic regression is 93%. Accuracy for linear SVC is 96%. Accuracy for SVC is 96%, and accuracy for nearest neighbor classifier is 96%. Fine. So that basically is the whole package or whole walkthrough how you can do simple machine learning in scikit-learn. Fine. So you just have to prepare data, create the classifier object, use the fit function to train, use the predict function to get the predictions, and then finally use some metric to get the particular metric, or interpret the results in howsoever form you want. Fine. Many a times the metric might not be available, then in that case you have to write that metric. Fine. So as I said earlier that I will also be discussing. So before I go that, Zubair sir, do I have time or?
Mm, Sir, how much time do you think it will take?
I think then I can give it as this is self-explanatory. The people can then understand this thing.
Okay, you can give a summary to them.
Fine. So as I told you earlier that when we use these different classifiers, they have some parameters to them. So just like the logistic regression or the SVM, it has the parameters like the penalty term, the C. Similarly, there could be what this what what do we say, what kernel are we using, or similarly what is the gamma value. So these things are, these are called as the hyperparameters. And many a times to find the right hyperparameter, we have to run different experiments. So just like to find this C penalty term, it could, whether it is 0.1, 0.0011, 1 or 1000. So for we set this value and then run it and see the accuracy. Then we change this value again, do the training, testing, accuracy again. Then third time so this is an involved process. So we are basically stuck in this loop of training, evaluating, training, evaluating, training, evaluating. So this loop is has to be run many times. So sklearn provides another convenient strategy for it, and by which we can learn these parameters or find these parameters in a very simpler way. So in order to find the hyperparameters, we just have to know 3 things, basically 5 things, but I have not mentioned the other 3. First is which estimator we have to find the hyperparameters. Fine. Second is what is the range of values from among which we have to get the best value. So just like in case of this SVM, we can find the correct value of C, or in case of the KNN, what is the number of neighbors we are finding for each test time. The number of neighbors could be 5, 4, 3, 2, 1, or 8, 10, 15. So that range we need to know. And then finally the question is, how do we then which strategy do we use to find the optimal or the best hyperparameter. So just like we can use a grid search, or we can use some particle optimization techniques, or the genetic algorithms to find that hyperparameter. Fine. So one of the one of such strategy is the grid search, in which what we do is we arrange the parameters in a grid form and then evaluate for each of them. It's kind of a brute force method. So here what I have done is I have imported this grid search CV object, and then I have created the parameters. So the parameters for the KNN I have created from 1 to 8, right? So whether we have to use the value of K as 1, 2, 3, 4 up to 8, I have arranged them in a list and then finally made a dictionary of it. So as we said, the grid search expects the parameters in the form of a dictionary. The first parameter to grid search should be the classifier. Then this then it expects us the KNN. Then expects the parameters. Then I have given us the number of jobs as well, and then finally the verbosity. When I say verbosity equal to 1, it will tell me what step it's doing currently. And then I have to run the fit function on it. So if I do it, you will see parallel 8 jobs are running. There is some error here in this case. Maybe I will use the linear SVC classifier. If I run it, so you see here, it ran it for, and then finally you can find the best parameters and the best score, just like I have done it here. CLF.best parameters, CLF. So for the best parameter is C equal to 6. Fine. So you, for a value of C, which is like a best value of C from on the range from 1 to 8, 6 gives us the best results of 0.96. Fine. So in this way, you can find the hyperparameters using this grid search as well. And that basically ends my presentation. If you have any questions, you can very well raise them or write them in the chats. Over to Dr. Zubair. Zubair sir, we can take over. Am I audible, Zubair sir? So if nobody has any question, then we can close this session.